So I'm Chandramali. I'm the course TA for this particular course. So basically, this session you can ask me some of your doubts related to this week's classes or some assignment problems, and then I can clear it. I have prepared. I'll be discussing about 10 questions, so that you'll be able to answer some of the assignment problems quite easily. But if you have any doubts, you can ask me now, so we can first discuss that and then go on to the problems that I have prepared. And if you unmute yourself and then ask the questions, it would be easy for me to discuss. Do you have any questions? Any doubts related to this week's class or previous week's class? Can you answer? I mean, you can even. Oh, okay. All right. I thought you're one of the students. All right. So then I'll wait for some students to join. So let's see. Maybe I'll wait for another five minutes. So then, if not, and then I'll start some of my things that I have prepared. Yeah. Sure. Yeah. Okay. Right. I don't see anybody joining as of now. Think like let people join in between. So I'll start discussing some of the questions that I have prepared. So first, let me discuss the let me discuss the sorry. uh, yeah, first let me discuss the some of the practice assignments. So as you can see here, first thing is related to the definition of entropy per se, or the second law of thermodynamics. So as you can see here, they are asking about what Kevin Planck's statement deals with. So as we know, Kevin Planck's statement is related to heat engine. Okay. So basically what we are going to do here is they talk about the conversion of heat into work. And basically, as you know, Kevin Planck statement tells that no effect can be no effect can be observed where the entire conversion of heat into work is observed. So basically, if you take some heat from the hot reservoir and then do convert the entire heat energy into a work that is basically 100% efficiency, or efficiency is one, which is not possible according to the second law of thermodynamics. Therefore, some heat has to be released into the cold reservoir. So that's what Kevin Planck's statement deals with. So basically, here it is related to the conversion of heat into work. So that's what the first statement deals with. Okay, so that's quite straightforward. And as you know, Clochier's statement is going to deal with okay, is going to deal with the refrigerator aspect of second law of thermodynamics, where you just cannot transfer heat from a cold reservoir to hot reservoir without any input of work. Okay, so it's just they are equivalents, but then they have been put forward in the context of heat engine for Kevin Planck statement, and a refrigerator in case of the Clochier's statement. Okay, so it's as simple as that. I'll just write it down here. Right. Just make it a little bit bigger. Yeah, done. So we have related to the second law of thermodynamics. Just a minute. Okay. What does happen? I think I'm still doing just a minute. This is one problem. Let me just should be able to do it. Yeah. All right. So as I was telling you, second law of thermodynamics, two statements were discussed. Two statements were discussed. One was Kevin Planck's statement. Wow. And this deals with conversion of heat to conversion of heat to work. And this is related to in the case of heat engines. All right. And second, there is a Cloutier statement, and that is basically transfer of heat from cold to hot reservoir, and basically that is your typical refrigerator. All right. So what's the next question? So here is, as you can see, there are different representations, and they're asking which of the following is actually allowed by the second law of thermodynamics. So let's draw each of these in the question, and then we'll discuss one by one. So this is related to practice assignment question 1. Okay. Now we have practice assignment question 2. We have different conditions. So A is basically we have, oh, sorry, A is basically this is TH, this is TC, and we have 900 Kelvin and 200 Kelvin over here. Oh, sorry, T1, T2. Yeah, make it T1, T2. So it's the same. T1 is 900 Kelvin, and T2 is 200 Kelvin, and we have condition here. So what was the condition over there? Shows work energy E is taken. So E is engine. You take some heat, give some heat, you do some work. So this is what they have represented over here, and this does not actually violate the Kelvin-Planck statement, as heat is taken from a hot reservoir and then heat is released to a cold reservoir and some amount of work is done. So basically this is does not violate. So this is allowed. Okay, so allowed. So this is allowed. So then what's the next one? Next is you have engine, sorry, you have a refrigerator where, okay. So then B is the refrigerator situation. Again, there is T2 is 200 Kelvin, T1 is 900 Kelvin, and then you have refrigerator. You take heat from the cold reservoir and you're giving heat. This does not happen because there is no work here, no work done, no W, so violates the Cloutier statement. Violates Cloutier statement. So not allowed. As simple as that. Right. So now what's the third possibility? Let's see. Again, it's I think the same temperature range. T2 is 200 Kelvin. T1 is 900 Kelvin. Okay, somebody has joined. Oh, sorry. Yeah. Yeah, nobody has joined. Anyway, so what is the? I'm sorry. I'll have to change this to intersection. Isn't it? Okay. So as you can see here, third one is again a refrigerator, but work is being done here. So here it's a refrigerator. Work is done, and then heat is being taken from a cold reservoir and going to a hot reservoir. So this is in line with Clausius statement. Okay, Clausius statement. So allowed. So this is allowed. So then we can just mark it over here. As you can see, first was allowed, A was allowed, B was, sorry, C was allowed, B was not allowed. So it's simple. Okay. So now just mark here as well. So this was not allowed, B was not allowed, C was allowed. Just push it down. So now we have to deal with the third question. So practice assignment question 3. So what is the question? As you can see here, the Carnot cycle, as Sir taught that in the class. So the process of a Carnot cycle comprise of which of the following options? Okay, two adiabatic and two constant volume process. There was no constant volume or isochoric process in the Carnot cycle, so this option is definitely not there. So then two adiabatics and two isothermal processes. Yes, that was present. Then two constant volume, again two isochoric, no, not at all. So we can ignore the A and C options. Then there is two isothermal and two isoentropic processes. So B and D seem to be, or C, both seem to meet the criteria. So let's see what's actually happening there. So I'll just draw the diagram, okay? Carnot cycle. First, let's draw the PV diagram. PV diagram. So as you know, first is isothermal compression, isothermal expansion, adiabatic expansion, isothermal compression, and then finally adiabatic, okay, where am I going? Finally, adiabatic compression. So this is the first one, two, three, four. So if you see here, this is isothermal expansion, isothermal I mean, I'll just write it as isotherm, adiabat, isotherm, adiabat again. So basically, you have two isotherm and two adiabatic. So option B is correct. There's an equivalent way of representing this. Oh, sorry. So this is in terms of PV diagram. But then we can also represent it as a TS diagram. Okay, somebody has joined. I'll just let them in. Okay. Hello, Jaydeep. Good evening. Can you see my screen? And am I audible? Hello, can you hear me? And I'm audible. Jaydeep, can you hear me? Hello.
Hello.
Hello, Jaydeep, can you hear me?
Yes, sir.
Okay, okay. So I remember you joined in the first TA session, right?
Yes, yes, sir.
Yeah, yeah. You're a UG student, first year UG student.
Yes, sir.
Okay. So, okay. So basically, what happened was nobody joined, so I started recording the video and discussing some of the questions. Since it's just two questions, I can discuss them again. And do you have any questions that you want to, ask before I proceed to the questions that I have prepared?
Yes, sir. I have some problem in
Okay.
that
In which one?
assignment.
Okay, which
Those
assignment?
week four.
Okay, in the week four assignment. So,
Yes.
I mean, which question in particular?
Uh, One.
Okay, just give me a moment. I'll share a different screen. Okay. Okay, okay. Yeah. So this is so I think you are able to see this. All right. You're able to see the screen, right? Hello.
Yes. Yes,
Yeah,
sir.
yeah. So this is the practice assignment. I was actually discussing some of the practice assignment problems. Now, in assignment 4, which question did you have doubts on? First one.
Sir. One.
One. Anything else? Did you have questions related to anything else?
Yes, sir.
Okay, which one? Question 1, then
Sir, I have a problem in question number two. Can you explain
2.
this?
Okay, I'll explain that. Okay, then anything else?
Question number four. These two.
4.
Uh, Two
The
and four.
isochoric process.
Yes.
Okay, anything
Of
else?
four. Is a Carnot cycle.
Okay.
2004.
Sorry, Carnot cycle. Where,
Yes,
I
sir.
mean, which question?
For which of the following figures shaded region does represent the total work done in the Carnot cycle?
Oh, the practice assignment.
Yes, sir. Yes.
Okay, okay. So I'm discussing all of those. So whatever you have told, I'll be discussing today. So I think you can just, I mean, okay. So did you have any problem related to, this problem, practice assignment question 2? Do you see the question 2?
Yes, sir.
Hello?
Yes, sir.
Yeah, I think your voice is a little feeble.
Hello.
Yeah, yeah, I can hear you. All right. So, question 4, right? I'll come to that.
Two and
Just
four.
give me a moment. I'll finish question 3
Okay.
and then I'll come to question 4. Okay?
Okay, sir.
Yeah, sure. Let me close it. Okay. All right. So basically, I was talking about Carnot cycle in question 3. So, as you can see, in Carnot cycle, we have, you know, two isothermal processes. First, isothermal expansion, then adiabatic expansion, isothermal compression, and adiabatic compression. So this is in related to a PV diagram, all right?
Yes.
So we can also represent this as a TS diagram, okay? So let's say you take here, since this is an first step going from state 1 to 2 is an isothermal process, temperature is not going to change, okay? So it's just going to be like this. But since heat comes into the system, it is going to expand, and therefore the entropy of the system is going to increase. Heat is coming into the system. So as we can write delta S is equal to integral D. Sorry. Okay. ds reversible path divided by T. Okay. So sorry, not ds, dq. dq. So since heat is going into the system and it's positive, you're going to see an increase in entropy. So x-axis is entropy is going to increase. So the next step is adiabatic process. So here in adiabatic process, what is the important thing? There's no heat exchange. Heat is not going to go into the system. Therefore, there's going to be no entropy change. Zero, right? So it will be a straight line downwards, and temperature is going to decrease as this is an expansion, adiabatic expansion. That is quite clear. So this is 3. Then again, it's an isothermal compression. Okay. So again, temperature is going to remain the same, but entropy is going to change. Since it's in compression, what's going to happen? Heat will come out of the system, which is negative. So this is going to be a negative value. And then again, last step, it's simple. Adiabatic, since it's adiabatic, the heat is zero. So therefore, there's no change in entropy. It's just the temperature is going to increase because it's a compression process. Okay, it's as simple as that. All right. So you can write like this as well. So what's happening here is there is so this is temperature is same, right? So this is again an isothermal process. Okay. And but here what is this? Temperature entropy is the same. So isoentropic process. So there are two processes, two isotherms and two isoentropic. So this is going to be isoentropic. I'll write it here. All right. So if you see here, if you see the question over here, this is basically both these answers are kind of correct. B is two adiabatic and two isothermal, and this is two isothermal and two isoentropic. So both of them are actually correct. But if I have to choose between these two, I would rather choose the D because this is a state function and this is not going to change. Even, I mean, sometimes we may not do it perfectly adiabatic, but we'll be able to do it perfectly isoentropic. Okay. So now, Jaydeep, so now we come to question 4, right?
Yes,
This
sir.
is the question where you have some doubt.
Yes, sir.
Okay. But are you clear with the Carnot cycle, isothermal, adiabatic, all those things?
Yes, sir.
Okay. So now in PV diagram, as you can see, all right, we can deconstruct it into different versions. Okay. So let me just draw it over here so that it's easier for us to discuss. Okay. Sorry. A, Q, 4. So now again I'll draw the Carnot cycle. This is the first process, right? Isothermal PV. Okay. This is the first diagram. One, two, two. So this is an isothermal expansion. Expansion. And so in isothermal expansion, what is happening to what is the work done on the system? Is it a positive work done or a negative work done? Gas is expanding, okay? Jaideep.
Yes, sir. Sir, I
Yeah,
think
yeah.
negative.
Sorry?
Negative.
Yeah, you're right there. Work is done. So in this case, since the gas is expanding, we are not doing any work on the system. Basically, the system is doing work, so it's negative, right? So now in from PV diagram, how can you get the graph? How can you get the work done? How do you get the work done from PV diagram? This is supposed to be a straight line down. Okay, so what is work done? Can you tell that formula?
W is equal to PdV.
Sorry? Yeah. What is that?
PdV. U
Ha,
plus PdV.
minus PdV, right?
Yes.
So since there are this a graph, what do we do? Uh, what do we do? We integrate, okay? So this you're clear with this, right?
Yes, sir.
Ha. So now in a graphical manner, what is this actually? PdV. What is the graph of this? What does this particular formula represent graphically? What is it? It is called area, area under the curve, right? Hello.
Hello.
So basically this is area under the curve, okay? So we need to treat it like that. Fine. So as you can see here, this is the first area. I will call this area as A1. All right. I'll just, okay, let this be there. So work 1 to 2 is basically A1. The area under the graph of this PV diagram. All right. Do you understand this?
Yes, sir.
Ha. So now what is the next process? Adiabatic, adiabatic expansion, right? Maybe I'll put it in some other color. I'll just put it in red, okay? So that there's some difference. This is adiabatic expansion, right? So that you're clear with that now. So again, drop this thing. All right. So again, work 2 to 3 is going to be, I'll call this area 2. Okay. And this is done. So both these things are work done by the system. Okay. Do you get that?
Yes, sir.
So this is basically work done by the system. Remember that alone. Both these are basically work done by the system as it's expanding. It is expanding. Okay. So now I'll then we'll have to I'll draw a new graph, otherwise, I'll do the next process then. Okay. I'll go to next page. Now we'll do the adiabatic uh, we'll do adiabatic. We'll go from point 3. So isothermal, what is this? Isothermal compression, na? So this is a PV diagram. So this is isothermal compression. Now, since it's a compression, we are going to do work on the system. Okay. And that work is going to be what? The area under the curve again. All right. So this is, I'll name it as A3. Let me put this 4 over here. So this is the isothermal compression part. Now, what's the last step of the Carnot cycle? What's the last step of the Carnot cycle, Jyoti?
Adiabatic compress.
Yeah. So this is the last step. So again, what is the, again, since it's a compression, we are going to compress it. We are going to do work on the system. And this is the area. Okay. So this I'll name as A4. Okay. So now I'll just write everything now. Okay. This is, sorry. This is work 3 to 4 is going to be A3. And then work 4 to 1 is going to be A4. Now, what I want you to do is, can you tell me all the signs? Okay, I want you to tell the signs. So the first two processes are expansion. So what is the sign for this? Expansion work is negative or positive?
Expansion is positive.
Sorry? Uh-huh. Your voice, I'm not able to hear you properly. Hello, Jerry.
Positive.
Ha. Expansion work. Come again.
Positive.
Okay, can you tell me the formula? Minus P delta V, right? This is the problem. This is the formula, correct?
Yes.
Ha. So now let's say it's an expansion. So volume is going to increase. Okay. Expansion V2 will be greater than V1, right?
Yes, sir.
Ha. So do you see this pressure V2 minus V1? Okay. So now since V2 is greater than V1, what is the sign going to be? What is it? Negative or positive? So this is a positive quantity. V2 minus V1 is going to be greater than 0. So again, there is a negative here. So what is the convention now? Work done as?
Negative.
Yeah, in expansion. So basically, whatever work we are talking is always work done on the system. Okay. So since system is doing, is going to be we are not doing any work. We are basically doing negative work. So this is negative, and then this is also going to be negative. Both these are expansions. Okay. So now let's come down. Here we are doing work, so it's going to be plus. Then
Yes.
this is going to be plus again. Now, what? Sorry. Hmm. So now, what is the total work done? It's just going to be summation of everything now. Work, sorry, 1 to 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 3, right?
Yes.
Sorry, 4 to 1, 4 to 1. So 4 to 1. So now work 1, 2, 3 is minus A1 minus A2 plus A3 plus A4. Now graphically, I want you to, what does this represent? It is going to be A3 plus A4 minus A1 plus A2. Now, what we'll do is, so since this is a Carnot cycle, the system is going to do work on, system is going to do work outside. We are not doing work on the system at all. So, whatever the system, in terms of system, it's going to be a negative work. Okay? Because we are not doing any work, system is doing work. So it is, I'll just keep it like this. So A1 plus A2 is going to be A3 plus A4. Now what is A1 plus A2 from the graph? You see this big area? This is A1
Yes.
plus A2, right? Now what, maybe I'll draw the diagram again so it's easy for us to. Ah, okay. 1, 2, 3, 4, 4. And this is the thing. Now maybe what I'll do is I'll shade it in different colors. Green first. So what is A1 plus A2? What I'm going to do is I'm going to first shade the A1 plus A2. Okay. This is A1 is still this part, and then again A2 area is this. This is A1 plus A2. Green is A1 plus A2. Okay. This is A1 plus A2. Now let me mark some other color. Maybe I'll take blue color. Blue color. So now blue color, it's not so great. Maybe some other color. Yellow probably. No. Yeah, yellow is much better. Yellow is the compression part of it. So that is A3 plus A4. So now what is now I have shaded the area now. So what is the work done by the system now? Let's just keep it as modulus, okay? So it's easy for everyone. So what is the work done? So this is the work, so this is the work done. This is the work done, work from the Carnot engine. Okay. Negative because work negative because work done by work done work done by the system. Okay. So now what is this area then? So what is W then? Jaideep, can you tell?
Um,
It is
only green shade. Only green
on,
shade.
only the green shaded region. So this, are you able to understand this?
Yes, sir.
This part is the W then. Okay. So if we go back to the question, so now which is the correct answer here?
A. 1.
Yeah, perfect. So that is the correct answer. All right. You understood this part, right?
Yes, sir.
Okay. So now finally there's just one more question. Which is the correct statement for a reversible process? A perfectly reversible process. So we are talking about the entropy change here. So basically the cyclical integration for a dq reversible by t is this is entropy basically. Okay. So now which is the correct thing for a reversible process? It's straightforward. It's the definition per se. It is which one? A, B, C.
A. A.
Yeah, that's it. Okay. I have marked all the questions. Have I? No. This was the correct answer. This was the correct answer. So now let's check submit. So all of these are the correct answers. Okay. Great. So now what we can do is we can go to some of the I have actually prepared some of the questions related to assignment problem. So this you had question related to first question, na? This enthalpy of reaction and all.
By second question, I have problem.
Okay. Then anything else? Fourth question.
Fourth question, sir, 1 minute. I want to see the.
Sorry.
Sir, here 6,
Sixth question. Is it? Sixth question. Okay. Then
6, 10,
okay. 10. Yeah. Then
and 13.
13.
Yes, sir.
Okay. Okay. Fine. We'll discuss. So actually 13th question. Okay, I'll come to that at the end because I discussed it before you joined. I'll discuss it again once again. Okay. So now we'll go one by one. So I actually have some prop. Okay, first let's discuss your second question. See. So this is one thing. So basically, in a bomb calorimeter, what we're seeing is delta V is 0. Basically, what? It's an isochoric process. Okay, isochoric process, a constant volume. All right. So now, what is an where did it go? What is an enthalpy? What is the formula for enthalpy? H is equal to what is it? U plus
PDB.
Jaydeep PV. Yeah. So now let's say what is delta H then? Delta U plus then P delta V, right? Plus V delta P. This process you understand, right? Because since there are two variables, we have to, first keep one constant and then see the differential for the other. Next, in the next, keep the other one constant and change it.
Yes, sir.
You understand that. So isochoric process, what is the thing? Delta V is equal to 0, as simple as that. So then this term is going to be 0, correct?
Yes, sir.
So delta H will be delta U plus V delta P. So it's just simple thing. That's all.
Okay, sir.
Okay. So maybe I can show you I can again discuss this problem. So 13th problem should be easy for you. So these are some of the questions that we saw in practice assignments. Okay. So this is related to the Kevin Planck statement and Cauchy's statement of second law of thermodynamics. As you can see here, Kevin Planck's statement deals with heat engines, where they talk about conversion of heat to work. So in simple words, it states that when you take heat from a hot reservoir, you cannot convert the entire amount of heat into work. Okay, this part you understand, right? Because if we are able to convert the entire amount of heat into work, efficiency is going to be 100%, which is not possible according to the second law of thermodynamics, correct?
Yes, sir.
So some amount of heat has to be released. So that is the T, it go to the cold reservoir. Now Cauchy's statement talks in terms of refrigerator, okay, where they tell that you cannot transfer heat from cold to hot reservoir without any input of work. Basically, if let's say without inputting work, you're just transferring heat from cold reservoir to hot reservoir, that is again not possible. Okay, you need to do some work. In our case, in refrigerators, the electrical energy is converted to mechanical energy to do that. Okay, so now there are certain things. So first you see here, the first thing is there is a hot reservoir 900 Kelvin, and then there is a cold reservoir 200 Kelvin. So then some amount of heat is taken, the engine is doing some work, and some amount of heat is released. So this is valid, right? Because it's satisfying the Kevin Planck statement, correct?
Yes, sir.
So this does not violate the second law of thermodynamics. So this condition is allowed. So now there is another condition where you see here, this is a refrigerator. R is refrigerator, and you have a hot reservoir, cold reservoir. You're taking some heat from cold reservoir and directly transferring to the hot reservoir. Is this possible?
No, no.
Because no work is done, right?
Yes, sir.
Correct. So you see here, basically here, this is again a refrigerator. Heat is taken from cold reservoir, put to hot reservoir, but there is a work component here. So is this possible?
I
Is
don't
this possible?
know. Sir, why?
Huh. So you see here, some heat is taken from cold reservoir and directly put to hot reservoir, na?
Yes, sir.
In the first case, there is no work being done here, but here
Oh, okay,
we
sir.
are we are doing some work, na?
Yes, sir. Yes.
Because of which this process can be made possible. Okay.
Yeah.
This
Okay, sir.
process, if you see here, this basically you're going from a cold temperature to a high temperature. You're transferring heat. This while this will basically decrease the entropy, which is not possible of the surroundings. Okay, of the entire process, the entropy of the universe will decrease here. But here, since you're doing work, the entire entropy of the entire universe will be positive. The change in entropy of the entire universe will be positive, which will allow the process to take place. All right. So now, if we go to your assignment problem, here you see here T1 is greater than T2. So this is the hot reservoir. T1 is hot reservoir. Okay. T2 is cold reservoir. Correct.
Yes.
So what are we doing here? We are taking some heat from T2, which is the cold reservoir, and giving to T1. Okay.
Yes, sir.
But what is happening here? Work is being done on the system, or work is being done by the system here. See the arrow mark and tell.
Honda system.
No, see the arrow mark. The system
It
is doing
means
work here.
yes, sir.
So, okay, we'll go to this. Here you see here, this is the same thing except that the arrow mark is towards the system. Basically, work is done on the system. Okay,
Okay, sir.
but
So
here,
by the system.
huh? So basically, what they're telling is refrigerator which is taking some heat from cold reservoir, transferring to hot reservoir, it not only does that, but is also doing some work. Is this even possible? First case only is not possible. On top of it, it's doing some work.
No, it's not possible.
Yeah, it's not possible.
Yes, sir.
But let's say if T2 was greater than T1. Okay, this is the hot reservoir, this is the cold reservoir. Then is this possible?
Yes, sir.
Because that is the heat engine, right?
Change.
Yeah. Okay. So now your question 2 and question 13 are done. Then question 6 you had. Okay. 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 Question 6. I'll come to that. Okay. We'll come to question 6 after dealing with question 4 and 5 because something related to that. So they're all related together. So you had doubt with question 1 as well, na?
No, it's no, sir.
No, no. Okay, fine.
One
So in
is
that case, maybe first I will discuss question 3 and 4 so that it's easy for you. Then I can go ahead to question 1 and 2 because you already know it. Maybe I'll just put it in recording. So first let's discuss question 3. This is actually related to question 6. Okay. Um, okay. So here you see here. Okay, I'll just change one thing here. Instead of I'll make it a common thing. N moles. So now we have N mole of ideal gas. So this is ideal gas. N moles. N moles. T1, V1, 2, T2, V2. Okay. So this is what we are going. So first thing is where we want entropy change. Okay. So tell me one thing. Is entropy change a state function or not? Do you know what a state function means? Do you know what a state function means? Okay. So basically, state function means it depends only on its position. Okay. It does not depend on the path taken. Fine. Let's say you have a PV diagram like this.
entropy is a
Sorry?
state function.
Sorry?
Entropy is a state function.
Yeah, exactly. So basically, entropy is a state function. Okay. Delta entropy change is a state function. It just depends. It depends on the
Current
initial and
state
final
of
position. Does not depend on the path taken. Okay.
yes.
We are going to use that to our advantage. So now we have T1 V1 going to T2 V2. Now can we split this process? Okay. We can split this process. Na? So what I'm going to do is construct a diagram like this. So first I have T1 V1. What I'm going to do is I will first do a isothermal process. Okay. Isothermal process. Isothermal process. So that means T1, but then volume is going to change. Okay. You get this? Then what I'll do is then I will make this a isochoric process. That means volume remains the same, correct?
Yes.
T2, V2.
Natural change.
Huh. So since I'm basically dividing this single process into two different process, and we can then use the already known I mean functions to derive the entropy change for this. Okay. So now for the first process, for the isothermal part. isothermal part. What is delta S? It is Q dq reversible by T, na? Huh? Dq reversible by T. Now, what is the what is the dq? Isothermal process, what is the change? What is the change in heat? Wait, tell me. What is dq? Nice thermal thing. What is dq? Okay. In isothermal process, okay, temperature is the same. Okay. So what is the change in internal energy for an ideal gas? Delta U is what in isothermal process? Okay, see, in isothermal process, in an isothermal process, delta U, since delta U depends only on the temperature, it does not change at all. So delta U is zero. Okay, and U delta U, just keep it like that, is going to be equal to, or else I'll keep it like this. U is equal to Q plus W, na? So basically dq is going to be equal to minus dw, correct? So if delta U is zero, let's say du, I'll make it like this. If du is zero, then dq is d minus dw, right? And w is basically, so dq, w is minus pdv. So minus pdv. And then for an ideal gas, what is pressure? nRT by volume, correct?
Yes.
So minus and minus will become plus. So then we have nRT by V dV. If we do this, if we integrate on both sides, sorry, I'll just, where is it? Okay. So this is the dq part. So now let's substitute this in the delta S equation. We have dq, right? So basically it became nRT by V, and we have a T here. So that, and dV. This will get cancelled. So now we can take nr as a constant, so we can take it outside. So delta S for the isothermal part, call it as S1. Okay, I'll keep it as, I'll put a subscript there. It's going to be nr dv by v. What is this integral? So it'll go in from v1 to v2. What is this integral? Integral dv by v is
V1 to V2 minus V1.
basically it is natural log, right? ln v v1 to v2. So delta S1 is going to be equal to nr
NR minus V1.
ln v2 by v1. Simple. This part is done. Okay. So this is one. So now we'll go to the second part, which is isochoric part. That is going to be easier. Isochoric part. So now I'll keep it as delta 2. Again, dq reversible by t. dq reversible by t. Okay. It's a constant volume process. Okay. So since it's a constant volume process, what is the dq here? dq is equal to constant volume process. Okay, I'll write it here. du is equal to dq plus dw, dq minus dw. So now constant volume, that means what is dv? What is that?
dv equal to 0.
So minus this term is going to be 0. So basically it's the change in internal energy, correct?
Yes,
So what is the change in internal energy going to be?
dq
Do you remember
equal
that? Cv,
dv.
remember that? Cv dt, na? Do you remember
Yes,
this?
yeah.
Cv dt, okay? Or else we can do it in a different way as well. You know, what is the internal energy of an ideal gas? 3 by 2 RT, na? So du is equal to 3 by 2 R dt, and 3 by 2 is R is actually the Cv.
See,
Fine. Yeah, anyway, both ways we can get it. Now what we'll do is we'll substitute this over here. We have Cv dt by t integral, and we are assuming that the heat capacity does not change over the temperature range of T1 to T2. That assumption is important. Okay. So again, you take Cv out, integrate from T1 to T2, dt by T. So what is this going to be? Sorry, I forgot one thing here. We have to put the number of moles. Yeah. What is that going to be? NCV ln T2 by T1, right? So this is the part for second thing. So since it's an state function, we can just add both of them. So total entropy change is equal to delta S1 plus delta S2. So your final expression is going to be something like this. Okay, delta S is equal to NCV ln T2 by T1 plus NR ln V2 by V1. Okay, so this is the general formula that we have obtained. All right, so now we have this. Okay, so basically this is your third problem. Okay, there they have 1 mole, so n will go out, and you have some answer. Now we will consider for isochoric process, and then we'll consider it for a isothermal process. Okay, you see. So now for isochoric process. So for isochoric process, what does it mean? V2 is equal to V1, correct? Volume is not going to change. So if ln1 is 0, this term will go off. Therefore, delta S is NCV ln T2 by T1. It's as simple as that. For 1 mole, it will just be CV ln T2 by T1. And that is exactly what we have over here. Okay. So what is this? What is the sixth question? If two equal quantities of ideal gas are mixed, then what is it given? Delta S mix of the okay. not actually given. Okay, so what we will do here is for this process, there are few things here. Okay, first is this: if you mix two ideal gases, it's going to mix. So this is more or less a spontaneous process. So delta S mix will not be negative. So first two options actually are negative quantities. Ln of less than 1 is going to be a negative value, and this is again a negative value. So that is not possible. Okay. So then what else? We have two options where they are positive. Now we need to find out what exactly they are. So thing is, we do not have the temperature from this thing. So what we'll do is we'll just assume that the temperatures are equal. Okay. So that is something that we're assuming. We are mixing two two ideal gases of equal quantity, of equal quantities. So that means volume A is equal to volume B. Fine. What is the entropy change? So let's assume first, assume TA is equal to TB. So therefore, just give me a moment. Let me think. What's this? Change into process. Yeah, we cannot use this formula. Okay. Okay. Jagdeep, hello.
Yes, sir.
Yeah, actually, I think I'll have to think about this problem a little bit because since the number of moles are changing, we cannot use this formula directly. Okay. So I'll refer some books and then get back to you related to this. Okay.
Okay, sir.
Maybe next week I'll discuss this.
Okay, sir.
Okay. All right. I'll have to think about this. Yeah. Fine. So then you also had problem related to Carnot refrigerator, no? The coefficient of
Yes.
performance. Yeah, yeah. Okay. So now, so the question is simple. What is the coefficient? So I'm just doing a related problem. Okay. But then if you understand this, you'll be able to answer that question. So the thing is, what is the coefficient of performance for a Carnot refrigerator? So it's quite straightforward. The coefficient of performance is basically, thing is, how much the idea is, for a certain amount of work that you put, more amount of heat has to be transferred from the cold reservoir, right? So that is the thing. So basically, what is the amount of heat you take out from the cold reservoir for a given amount of work? So that is the coefficient of performance. All right. So now this can also be shown that beta can be given as Tc by Th minus Tc, because you see what is the work going to be? Work is going to be Th minus Qc. Sorry, Qc. You see here, this is your refrigerator. This, I'll put it as Th, put it as Tc, and you do some work. And this is Qc, and this is QH. In a Carnot refrigerator, to release amount of QH over there, you will have to do QH minus QC amount of work. So this is the work that's going to be done, because QC plus W is going to be equal to QH. All right. So this is the work. Then you can actually, okay, maybe before coming to this part, I'll just, so you divide the numerator and denominator by QC, you will get QH by QC minus QC. I'm just, okay, everything there is a modulus. Sorry, 1. No? And you can show that QH by QC is equal to TH by TC. It's as simple as it. So then eventually when you go here, you will have something like this. TH by TC minus 1. So multiplying everywhere by TC, you will have something like this. Okay. So this is what you will have. So this is your final formula for coefficient of performance. This is for the cooling effect. So what we have 200 Kelvin and 400 Kelvin. So let's say what is the case here. So TH is 400 Kelvin and TC is 200 Kelvin. So here it's 200 divided by 400 minus 200, which is equivalent to 1. So see, understand one thing, that this is something called coefficient of performance and it is not efficiency. So in this case, coefficient of performance, coefficient of performance can be more than 1. That is something that has to be kept in. This is in case of refrigerator. All right. You got this idea? Okay, Jaideep?
Yes.
Okay, fine. So that's it. If you have any other doubt, I can clear. Otherwise, you can uh, you can leave and I'll continue discussing some of the questions. If you want to stay, you can stay and listen. All right.
Okay, sir.
Okay. So continuing on the same line, we'll just first see the efficiency of a Carnot engine. Again, it's quite straightforward. Eta is 1 minus C by TH, right? So let's say here TC is 200 Kelvin, TH is 400 Kelvin. So if we just directly, we can just substitute in the formula. It's going to be 40. This. So eta is basically 0.5, which is 50%. This is an engine which is 50% efficient, which is quite good, to be honest. You see, this is such a high range of temperature that we are talking about. We generally have much lesser range of temperatures to work with. So probably this is not the best things. Best of conditions. We generally have much lesser efficiency with all the engines that we are currently using in cars now. So this is good. Yeah. Now all these questions are done. We can go to the first two questions, which are related to enthalpy of reactions actually. So given any, let's say you were given any chemical reaction, what we need to do is we need to find the enthalpy change in a given chemical reaction. Okay, it can be a standard enthalpy of change, standard enthalpy of formation, or standard enthalpy of a reaction in a if the conditions are standard. So actually here it's going to be standard because it's 25 degrees Celsius and 1 atmospheric pressure, which are the standard conditions. So now what we have is N octane, 1 gram, and oh, writing N octane, and that's in gas, and it is we have H2O as liquid and CO2 as a gas. Now let's balance the equation. So what is N octane? It is C8H. How many? What is the formula? 8. So it's going to be 16, 22, right? I'm writing it correctly. Yeah. CH3, 2 CH3, 6. Yeah, correct. To be equal to octane. Oh, okay. Right. CO2 gas. Balance afterwards. I also have to put, sorry, I also have to put oxygen because it's burning. Okay, so oxygen is involved, of course. That is produced. So first, how many carbons? 8. Then how many hydrogens? 11. So 8 into CO8, 16 O2s, 16, sorry, 16 O, then 16 plus 11 is 27 O. So it's 27 by 2. Okay, I think that's balanced. That's enough balancing, I guess. So what is the standard enthalpy of this reaction? So it's going to be standard enthalpy of this reaction is going to be equal to, so enthalpy of formation of products minus enthalpy of formation of reactants. So, by the way, this is for one mole of octane. 1 mole of octane. We'll have to finally do it find for 1 gram. So that we'll do at the end. So here first for products, right? So it's going to be 8 into delta FH CO2 plus 11 into delta 11 11 into delta FH for H2O minus the 1 is for octane delta F octane, just put octane, and then minus 27 by 2 delta FH for O2. So now we need these values. I actually have a table over here. Let me pull out the table. This is from a book called Tinoku. This is again used. It's a physical chemistry textbook. So here we have a bunch of delta H formations, delta S knots, and delta Z. This is Gibbs free energy change. So now we need to find out R values. So H2O liquid, as you can see, the value is minus 283.83. Sorry, minus. Let me just note down all those values. Delta formation standard is minus 285.83 kilojoules per mole, right? Let me check. Yeah, kilojoules per mole. Kilojoules per mole. So then we have this for water, then CO2. Where is CO2? O2 is going to be 0 because that's the most stable state. So it's going to be 0. Where is CO2? So hydrocarbon. Okay, hydrocarbon is octane, octane, octane. Yeah, in octane. What is um, 6 to the. Oh, yeah, sorry. I was wrong. I balanced it wrongly. Shit. 6 to the. Yeah. 6 to the 12, then plus 6. 6, 18 to change all these. Then 9 only. Then 16 plus 9. 16. Yeah, 16 plus 9 is. Oh, we done. 16, correct. Plus 9. 25. Am I doing it correctly? 9 is 2. Correct. So this is 9. This is 24. Okay, let me check. This is 8 to the 16, correct? Plus 9, 25. 16, yeah. Okay, so now octane we need to find out. So delta H F octane is equal to, what was it? Minus 208.7. Minus 208.7. Now we need CO2. There is CO2. Gas. Organic compounds. Organic compounds. CO2. Seriously. That must be here somewhere. Gas. CO2. How come CO2 is not there? Oh, it is. Seriously, it's not. Oh, it's here. Okay. Minus 393.51. Then delta CO2 is minus 393 point. What was it? Minus 393.51 in kilojoules per mole. Kilojoules per mole. Okay, we have all these things. So now basically 8 into 39351 plus 9 into minus 285.3. So this is for water. H2O liquid. Then minus octane. So it is minus 208. 208.7. Of course, it's going to be, this one is going to be 0. So let's do the calculation. I'll just get my calculator out. Eight into minus 303. 393.51. And this 2 plus 9 into 285.83. Good. Yeah. So that is, this is minus 7572055 plus 208.7. What's that? Plus 208. Sorry, minus here, right? 208. So basically, delta H formation, sorry, delta H reaction is going to be equal to 5515.85 minus 5515.85, correct? Sorry, 5511.85. Now this is for 1 mole of octane. Now we need to find out this. So the above thing, that value is for 1 mole. Above value is for 1 mole. Now we need for 1 gram. 1 gram. Okay. So we need to find out the number of moles in 1 gram, which is basically N is equal to 1 by what is the molecular weight for octane? 8, 8 to 12, 18 to 1, 26. 114. So basically, we just need to multiply delta R reaction for 1 gram octane is equal to 1. We just need to multiply by 114, that value. Just to divided by 114, which is equal to minus 48.35. 48.35 kilojoules. So this is the enthalpy change in the reaction. Okay, so that's the final answer. So we have another question which is again similar. Okay, so in this question we need to find out the heat evolved or absorbed. Basically this is the enthalpy change. Here we're talking about, so basically this is enthalpy. I'm telling this is enthalpy change because in constant pressure and constant volume, PV is, there's no PV work, so it's just going to be the change in internal energy, which is going to be the heat. So here we have aspartic acid, just write ASP, 1 mole. Okay, it's converted to alanine, again 1 mole plus C, that is in gas. Okay. So actually this, you don't have to worry about it, because if you see the structure, it's a kind of balanced only. Because you see the structure, see aspartic acid H, and there's a side group COO minus NH H3 plus, and then if you see here, it's going to be CH3 COO minus, right? So this is aspartate. All right, alanine is again simple. So see here, CO minus H3 plus CH3. So this is alanine. So it's just the only difference is COO minus, and then that's going to be released as carbon dioxide gas. So there's not a problem here. Okay. So just erase this. So it's kind of balanced only. So we don't have to worry about anything over here. We just need to find out the delta R for reaction. So that is again straightforward, right? Because all we need is delta H formation for alanine plus delta H formation of CO2 gas, and then minus, okay, I'll just put gas also here, gas minus delta H formation of aspartate solid. Now let's look up the values and then we can just subtract after that. So first is it's an organic compound, hydrocarbon is organic, aspartic acid, yeah. Aspartic acid, delta H formation is minus 973.377. 973.37. So that is aspartate minus 973.37. Then we have need for alanine, right? L-alanine, so it says minus 562.7. Minus 562.7. Minus 562.7 plus, what is carbon dioxide thing? We already wrote it down. Minus 393.5. 3.5. Let's just check if all these are in kilojoules per. Yeah. So then we can just go ahead now. Just simple math. Let's just add it here. Okay. Have 973.37 minus 562.7 minus 393.51. Okay. So this is an endothermic reaction. It's per mole. So basically this is an endothermic reaction. Okay. Which implies endothermic, and they have asked us in kilocalorie per mole, right? So the conversion factor is quite simple. We know that 1 kilocal per mole is equal to minus 4.2 kilojoules per mole, approximately. Let me check. Let's just check once. Kilocal to kilojoules. One, okay, need to be accurate. Minus 4.18. We'll keep it rather. So we just need to divide it. So directly delta is equal to 17.16 divided by 0.184. So basically it's going to be 4.10 kilocal per mole. Kilocal per mole. Okay, so simple. That's the thing. So that is for the A part. Now we do have a B part where we need to write down. Okay, this is at 25 degrees. Now what is the thing for 50 degrees? That's the question. So it's going to be simple actually. Let's say I do this. So we have the same reaction. I'll write it down again. Aspartate is going to give to aluminum. Just write like this. Plus CO2 gas. This is at 25 degrees, okay? 25 degrees. This is delta R H 25 degrees. Now we have the same reaction at 50 degrees. 50 degrees Celsius. Same thing. Plus CO2. This is delta RH at 50 degrees Celsius. Now what we'll do is, to get this, we'll just do conversion. Okay. So this is isothermal process. Here we are just increasing the temperature. Oh, sorry. Since enthalpy change is a state function, we can, you will construct a cycle like this, and then find out. Okay. Since the final thing, basically we are going through this process. Since the final reactant is the same, the entire enthalpy change is going to be zero. Okay. But then we have many steps here. So first is the delta reaction. All right, 25 degrees Celsius. Next, we have the conversion process. That's the temperature change. So what is it? We have two products here, right? So for each of them, we need to know the Cp. This is happening at constant constant pressure. So it's Cp. So Cp of alanine into T, I'll just write, okay, I'll write T2 minus T1 only. And then similarly Cp of CO2 gas, T2 minus T1. Okay. Then what's the next process? This is the reverse of this. So basically minus delta RH, 50 degrees Celsius. Then Cp of aspartate. Now it is going from 50. So it's just T, oh sorry, going to T1 from T2. Simple. So we need this quantity, right? So we can just take it to the left hand side. It's 50 degrees Celsius is going to be equal to delta RH at 25 degrees Celsius. And then we can just make it this way. We can take T2 minus T1 as common. Then we have Cp alanine plus Cp CO2 minus Cp aspartate. Simple. Because we have just inverted this, so minus sign over here. So basically, what is this quantity? We'll define this quantity as the delta Cp. That is the difference in Cp between the reactants and the products. Okay. So this is delta Cp. This is products. So basically, I'll define delta Cp. P is Cp products minus Cp reactants. So that's what we have here. So finally, this is the equation that we get. 3 degrees Celsius is equal to delta RH at 25 degrees Celsius plus 50 minus 25 into delta C. So this is the final equation that we get. If we know this value, we can solve this question. Okay. Right now we don't know this value, so we'll just leave it at this place and then finish it off. Right. Now let me go back. Stop sharing. Go back to the meeting. Yeah. So Jaydeep had left. I don't know when he left. Okay, anyway. So right now, so these are the questions that we have discussed. If you see all these questions, I mean, if you understand whatever I have told you, you will be able to answer most of the assignment problems. And then it's straightforward from there. So let's see, next week we'll discuss questions related to assignment 5 and let's see. Okay, thank you.